This experiment sought to shed light on quantum topics, including the speed of light, black bodies, and emission line spectra. In this experiment, there were three separate but related investigations of light. In the first phase of the experiment, we determined the speed of light. And as you'll see above, I included the pop culture reference of Star Wars because they were known to travel by light speed. But what does that mean? In the second phase of the experiment, line spectra of hydrogen and deuterium were used to calculate the corresponding Rydberg constants, which were then used to find the mass of deuterium. And in the final phase of this experiment, we investigated black body radiation and the corresponding temperature of black bodies. So why would we care about studying light? Well, it can be used to model subatomic particles such as the electron via the principle of wave-particle duality, in which we know that both electrons and photons can behave as waves or particles. Light can also be used via emission spectroscopy, similar to what was done in this experiment, to identify unknown substances. Two hypotheses were put forth prior to the start of this experiment. The first hypothesis stated that deuterium will have a larger Rydberg constant than hydrogen. And this can be expected because hydrogen has a smaller reduced mass, which relates to the Rydberg constant, as I'll show later. And therefore, deuterium will exhibit higher energy and shorter wavelength transitions. The second hypothesis put forth is that the incandescent bulb will be the closest approximation of the three different light bulbs to a black body. And this is due to the way that the incandescent bulb works is that it has a filament, which when the filament is heated, it gives off light. In the speed of light phase of this experiment, a laser was pointed from the source towards two detectors via the use of a beam splitter, a movable mirror, and a focusing lens. And as we see in this slide, several measurements were taken of the distance between these different pieces, which would be important for the speed of light determination. And then here we see the experimental results, which gave an average experimental speed of light of 2.6 times 10 to the 8th plus or minus 1 times 10 to the 7th meters per second. And on the right-hand side are two sample oscilloscope readings for runs 2 and 5, in which we see that the oscilloscope renders the time difference, which was used to calculate the speed of light, via two different pulses. So the first peak is the first pulse, which was detected at detector 1, and then the second peak is the pulse which was detected at detector 2. So going into these results, we see good agreement of the calculations. All of the experimental speed of light values are within close proximity to one another, but there were some potential errors in this experiment. For example, the experiment was not conducted in a dark room, so there was outside light that could have interfered with the detection of the laser, as well as potentially scratches in pieces of the setup. So some future improvements that could be useful are to change the environment, to have it in a darker room, to take more measurements, and to increase the distance of the measurements. So in this experiment, we only moved the movable mirror up to 20 feet, so that could be increased to maybe 40 feet to gather more data. The second phase of the experiment involved two discharge lamps, one for hydrogen and one for deuterium, as well as two separate slits and a monochromator and photomultiplier tube detector. The spectra that were rendered from this experiment shows the energy level transitions for both hydrogen and deuterium, in which deuterium is the smaller peak on the left at higher energy, lower wavelength transitions, and hydrogen is the peak depicted on the right at the higher wavelength transitions. But how do we know which energy level transitions we were investigating? So the experimental wavelength range for the emissions was about 380 to 485. And based on the known Balmer series of the hydrogen atom, we can see that those wavelengths coincide well with the n equals higher level to n equals 2 energy transitions. The maximum experimental wavelengths were extracted from the raw spectra and plotted against the inverse energy level transitions in order to determine the Rydberg constant, which is the slope of the corresponding graphs as shown. And in addition to the experimental Rydberg constant, the procedure also led us to determine a theoretical Rydberg constant using the Bohr equation shown on the right. There was a very small percent difference between these values, which seems to point to a good sound experiment. In addition, we use these Rydberg constants to determine the mass of deuterium using the equation shown on the right. The experimental mass was determined and then compared to a theoretical mass, which was predicted to be about twice that of hydrogen, which is a known value, based on the fact that deuterium just has one more neutron than hydrogen. And likewise, that percent difference was 15.84, which is pretty good. There is very good agreement between the experimental and theoretical values in this experiment, given the small percent differences for both the Rydberg constant calculations and the mass of deuterium calculation. However, errors were still possible. For example, the photomultiplier tube voltage may have been too low, so it would be advantageous to adjust it to determine what the best applied voltage would be for this experiment. Additionally, the slit width could be adjusted to give more discrete line-like peaks rather than the broadened peaks that we see in this experiment. Overall, though, the general hypothesis that was set forth at the beginning was proved. Deuterium did have a larger Rydberg constant than the hydrogen. The third phase of this experiment investigated black body emitters by using 3 different types of light bulbs, an incandescent LED and fluorescent bulb, as well as a fiber optic cable and the Logger Pro software. The resulting experimental spectra are very different across the 3 types of bulbs. As we can see, the fluorescent bulb exhibits much more discrete line-like spectra than the LED, which is slightly broader, and then the incandescent, which is very broad. The maximum emission wavelengths of each bulb was then used to determine the temperature by the Wien equation shown on the left, in which B is just a constant. The raw spectra were then manipulated to create the Planck-fitted spectra as shown in the figure below. And the Planck-fitted spectra is different because it now accounts for the quantization of energy by using the H in the equation at the bottom, which is Planck's constant. And as we can see, this does affect the temperatures. But overall, the incandescent has a relatively high temperature compared to what the Wien equation initially predicted. How is it possible to know which of the 3 bulbs is the best approximation of a black body emitter? When the raw spectra is fitted to the Planck adjusted spectra, it is evident that the incandescent bulb has the closest fit. And when compared to an almost ideal black body, the sun, as depicted in the left part of the figure, we can see a lot of similarities between these two. Additionally, it's important to note that the Planck calculated temperatures of the LED and the incandescent bulbs were the same. However, it was evident that the incandescent bulb experienced a much larger range of wavelengths than the LED bulb, which is another characteristic of a black body emitter, is that they have a very large wavelength range. In this phase of the experiment, it was proved that the incandescent bulb would be a closer approximation of a black body emitter than either the LED or the fluorescent bulbs. However, there was still potential error in this phase of the experiment due to the presence of exterior sunlight. An improvement for this experiment may be to conduct it in a more controlled, darker environment, and it would also be good for analysis purposes to obtain a raw spectrum of sunlight. So to conclude, light enlightens us. In the first phase of this experiment, the speed of light was determined to be about 2.6 times 10 to the 8th meters per second. In the second phase of the experiment, hydrogen and deuterium emission spectra were used to determine atomic properties, including the Rydberg constants and the mass of deuterium. And then finally, the incandescent light bulb was determined to be the closest approximation of a black body emitter given its temperature dependence. Therefore, learning about light is lit. Thank you. I would also like to thank my co-collaborator, Joaquin Gotera.